with a long A.
Recommend you put it on your left side, just because.
Yep, yep, yep. Oh, let's switch it on and it'll work. Yep. Do I need to switch it on?
Nope, it's on there.
Oh, okay.
Morning, everyone. So today's speaker is Dr. Thomas Meier. He did his PhD in Leipzig with Professor Hase, and last year he got a couple of prestigious German government awards. And he will talk about MRI today at high pressures. Enjoy.
So, okay, hello everyone. So as Irina already told you, today I'm going to talk about our most recent developments in the field of high pressure NMR and diamond anvil cells. A topic I've been actually already pursuing since 2011, so it's already been 8 years by now. But today I'm going to talk about predominantly about what we've done over the course of the last 3 years in the Bavarian Geo Institute, where I started my postdoc. So I basically need to split my talk into 2 parts, whereas in the first part, of course, I need to basically review the main technical aspects we need to think about when we want to solve the issue of NMR in diamond anvil cells. Whereas, of course, the second part will be more about applications, where in the first part, I want to predominantly talk about our most recent experiments on metal hydrides. Then I want to briefly go over first homonuclear decoupling experiments, so a step towards high resolution NMR, then about something about our preliminary results on high pressure hydrogen, and in the end I want to talk about our recently developed tabletop NMR system. So let's directly start. So when we are thinking about NMR, the most basic NMR experiment works like that. So imagine you're having an NMR coil, which is part of an LC tank circuit. So now if we fill that coil with a paramagnetic or diamagnetic sample and switch on the magnetic field, for example, along the Z-axis, we know that a small amount of the nuclear magnetic moments will be polarized and begin to precess along this magnetic field axis with a certain frequency. And now in NMR, we are doing a small trick, which is we are feeding in a high frequency current into the coil, which generates an additional magnetic field, which has more or less the same frequency as the Larmor frequency. And with that, we are able to perturb the spin system. And we can, in principle, flip it in an arbitrary angle. So, and then if the pulse is gone, we are basically observing this back equilibrational process, which you can in principle see here. And then on our NMR spectrometer, we are in fact observing the longitudinal, the transverse part of an induced voltage of our spin system in our coil, which basically then looks like that in an NMR spectrometer. So we basically just add these things up and do a Fourier transform out of that, and we end up with our NMR spectrum. So, and while this experiment seems to be quite straightforward, there are already 3 main observations we can do. Whereas the first one and the most important one is, of course, to find the resonance in the first place, because that typically gives us a good indication about the electronic environment of a nucleus. For example, if we are looking at metallic systems, we are measuring the so-called night shift, which is a direct measure of the density of states of conduction electrons at the Fermi energy. On the other hand, we can also have a look at relaxation times, which gives us an indication about the energy dissipation in the system. And of course, it's always a good idea to look at the overall line shapes, because especially in the case of quadrupolar nuclei, we can get a good idea about the electronic or chemical environment of a nucleus. So, and now, of course, when we want to think about NMR in a diamond cell, we also need to think about the following issue, which is NMR is typically considered one of the most insensitive spectroscopic methods you can have. in order to illustrate that, imagine you have 2 million spins and you're subjected to a magnetic field of approximately 12 Tesla, which is actually already quite a lot. But even then, you're only able to polarize 80 spins out of that. So you would only do NMR with these 80 spins. So which basically gives you a rough idea that we are, in fact, always dealing with signal-to-noise ratio in NMR. And the SNR is basically proportional to 5 different processes or effects, where we have a squared dependence with the Larmor frequency, and of course we can improve SNR by basically going from low field to high field. This is something the NMR community is doing constantly. They are always increasing field strengths. If you have the money, if you have the lab space, and if you have people who are willing to maintain such a magnet, then that's fine. Typically, that's not the case. On the other hand, you can also try to play around with the nuclear polarization of your sample. So what you're doing there is you basically irradiate your sample with so-called hyperpolarized nuclei, which transport some of their spin polarization towards the signal, towards the sample, which also leads to a significant enhancement of the sensitivity. And then, of course, you can do the most straightforward thing, which is basically done by the physics community quite often by basically cooling down everything. That is enhancing the spin polarization on the one hand and reducing the thermal noise voltage in your RF components. And then there is this ominous factor of the filling factor times the so-called coil sensitivity. And that basically boils down towards the question of how can we actually miniaturize our RF components. Because it turns out that we can, in fact, do NMR in more or less macroscopic coils of about 2 millimeters in length and about 0.5 millimeter in diameter. And we can also do NMR at significantly lower sample volumes, for example, with these lithographically printed coils, which are only 0.5 millimeter. And of course, we can also do NMR on single NV centers in a diamond. So, and if we run the numbers, it turns out that we can actually kind of forget these 3 methods, because the gain and sensitivity we would get, for example, by going from 1 Tesla to 20 Tesla, is by far not as much as the gain of sensitivity we could get by simply reducing the sizes of your resonators. So, and this is basically the way we are following in BGI and our diamond cells. Because here what we are doing is we are using so-called magnetic flux tailoring. This is a fairly new and recent development in the field of NMR. And this is basically developed by an NMR engineering group in the Karlsruhe Institute of Technology. And the main thing we have here are these kind of 2-dimensional structures. These are so-called lenses after Lenz's law of induction. And they are basically, they can be built by, for example, a very straightforward laser cutting system out of very thin gold foil. And the experiment itself then works relatively straightforward. So you're placing one of these lenses in plane with an excitation coil, and then you can pulse into the excitation coil. Of course, the magnetic field will be coupled into the lens because it is also a conductive material. And then we are having a ring current building up in the outer diameter of our lens, which travels, for example, in that direction. And then at some point, of course, it is forced to enter this inner part. And now we have the nice situation that the outer diameter and the inner diameter are basically counter windings to one another, which leads to a very nice cancellation of the magnetic field between outer and inner diameter, and at the position of the B1 field energy in this inner part of the lens. So one of the first experiments where we basically saw that works was also put forward by the group of from the KIT people. Here they basically used such kind of a resonator, dipped it into water, and measured magnetic resonance imaging across a fixed axis, and measured the SNR per pixel. And as you can see, depending on how small we are making this inner diameter, we can actually enhance the signal-to-noise ratio per pixel quite a bit. So having this having this at hand, we immediately thought that that might be very, very useful if we are able to do that in diamond cells. So after a couple of weeks of playing around, we came up with the following setup. So we started out with an indenter cell where we're having an 800 micrometer diamond on the one side and a 250 on the other side, where we are placing this kind of resonator structure on the 800, so the lens on the 800 micrometer colored, and the excitation coil on the pavilion, and then we're pressing down everything with the 250, of course. So the first cells have been prepared with paraffin oil because it typically gives out a very strong hydrogen signal. And this is the first proof of principle experiment. So pressure in these cells might have been very close to ambient conditions, so 1 or 2 GPa. And if we compare the case where we are using a lens with the case where we're using no lens, we can see that after a single scan, we can already boost the signal-to-noise ratio by approximately 4 orders of magnitude, which is, of course, a step in the right direction. And now you might ask, how can we expect something like that to be stable under high pressure? And it turns out that that's actually not a big issue because we have been able to pressurize these cells up to 72 GPa. And all of the spectra you see here, so from 1 GPa upwards, are all single-shot signals. So there's no accumulation involved whatsoever. So the actual spin sensitivity of these resonators can actually be considered quite good. So, and after we've been able to publish these results in Science Advances in the end of 2017, we of course thought that it might be better even to combine physical vapor deposition techniques with FIB milling. And this is exactly what we did. So we took 2 diamonds having symmetric colors, covered them completely in copper of approximately 1 micron. Then we put these diamonds into a FIB and cut out shapes like that we have 2 lenses per diamond, where we have the first stage lens sitting on the pavilion of the diamond, which picks up the magnetic field of our excitation coil and transports it very close to the cullet, where we have another step of induction towards the second stage lens, which then leads to a significant enhancement of the B1 field in this inner part. If we do that on both sides and combine the excitation coil towards a Helmholtz coil, we can actually achieve quite a strong and more or less homogeneous B1 field excitation in our sample cavity. So, and here you can see some photos of our SEM cutting and of our FIB cutting. And as you can see, using a FIB, we can actually control the geometry of these lenses to a very satisfying degree. So, of course, we can go one step further and use beveled diamonds by simply introducing a third step of induction, where we are having now 3 lenses per diamond on the pavilion, on the beveled area, as well as on the cullet here. Again, if we do that on both sides, we have to deal at some point actually with 6 lenses, which is a bit messy, but especially in the preparation stage, because as you can imagine, these copper layers are actually quite fragile. But if you are able to prepare such a cell, you can go and pressure up to, well, we reached a 200 GPa recently with a pair of 100 micron diamonds. So, and now in order to get everything into perspective and from an NMR point of view, I prepared that kind of figure. So here there are a lot of things going on. So the y-axis measures the so-called time domain limit of detection, which basically tells you how much spins do you need in your sample cavity in order to get a signal-to-noise ratio of 1 after a single shot. So, and here on the x-axis we have a logarithmic pressure scale. So, and the first thing we need to recognize is that standard NMR sensitivity is in the order of 10 to the 21 spins. That means a static experiment without magic angle spinning, without dynamic nuclear polarization. You are just making a coil, put something in there, and measure your signal. And as we can see, already going one step into diamond anvil cell research, we can already significantly enhance sensitivity with a lot of high pressure approaches. So for example, the work from Takao Okuchi, who did his work here in the beginning of the 2000s, plot somewhere here. The split gasket from Isaac Silvera is also somewhere around here. Yes. And the second group, which we have here, this is already a step towards a miniaturizing RF components, because this is basically what we have done where I did my PhD with microcoils. So these are very, very small coils, which we put directly in the sample cavity. And the good thing about that is that at ambient conditions, it's actually perfect. We are able to increase sensitivity by approximately 4 orders of magnitude, which is nice. But unfortunately, as you can imagine, having the coil directly between the diamonds is actually not so good for the coil itself, because the coil basically ceases to be a coil even within approximately 5 GPa of pressure, which is actually the reason for this strongly deteriorating sensitivities here within each experimental run. Whereas on the other hand, the lens-lens resonators, which basically plot somewhere around here, are not only 2 orders of magnitude more sensitive than even the microcoils. No, they are also quite stable under pressure, as we can see here, with pressures which are basically 1 order of magnitude higher than what you typically get on average with the other approaches. So now the biggest question is, what can we actually do with that? So yeah, it's of course a 10 orders of magnitude sensitivity enhancement. So now the biggest question is, what can we do with that? And one of the first experiments we have done was on high pressure ICES, because, oh yeah. Yeah. We put it in a normal magnet. So it's basically relatively straightforward. We have a home-built probe. So we fix these pressure cells on our probe. Then we put the probe into a magnet and measure standard NMR experiment. There are, of course, a couple of things you need to you need to keep in mind. For example, don't use 2 kilowatts to pulse in that, because you're basically grilling your coils. And also some other things, for example, shift referencing can be a bit difficult because you have a big chunk of metal around your coil. So you basically need to be a bit careful in that sense. But apart from that, it's not too much different from what you typically do in an NMR experiment. Yeah? Kind of depends. So typically with the microcoils, it's extremely straightforward. The smaller you get your coil body, the shorter you get your line. So with the microcoils, we typically had 1 micron, half a micron at 20 watts. So with the lenses, of course, everything is driven by the excitation coil, but it's still quite short. So like 3 to 5 microseconds at like 50 watts. So it's definitely much lower in terms of wattage than what you should use for like microscopic coils. Yep.
What is a I mean, we know what a magnet is. We know what.
Yeah, it's the.
So it's a holder.
Yeah, it's kind of a stick with 2 capacitors at the end. So that's everything there is. Of course, when you have commercially available NMR probes, they are much more than that. But our home-built ones are basically just a tube and 2 capacitors and then the cell, because we don't need anything else. But other probes are like much more difficult when you have like when you want to pulse at different frequencies. Your probe can be very quickly filled with electronics. But we typically don't have that. Okay. So now let's come to the application part. So again, one of the first things we had a look at was high pressure ICES. And of course, we all know the narrative behind that, because if we start out at I7, we know that the energy potential has a double well minimum with a finite possibility for the protons to tunnel from that minimum to the other minimum. And these tunneling processes actually are known in NMR to already have a couple of observable phenomena. For example, relatively straightforward, you would expect something like that to have some kind of effect on the general line shape, so we would expect some kind of dynamical averaging. On the other hand, depending on where the hydrogen sits at some point closer to this oxygen or even in the midpoint, you would expect some kind of effect on the chemical shielding. So the chemical shift should also be very sensitive for the position of the hydrogen. And also in another respect, these tunneling effects actually do induce forbidden transitions at low field NMR, which we can barely see at high field. And if we have a look at the actual data, we saw in the chemical shift dependence basically two transitions, one at 20 GPa, where the chemical shift shot up by approximately 50 ppm for protons, which is actually quite a bit. And this is often regarded as a transition from a high barrier to a low barrier hydrogen bond regime. And then we also saw a second surprisingly sharp transition at approximately 75 GPa, which we took as the transition towards this symmetric H-bond regime. Whereas on the other hand, if we had a closer look at the resonance spectra themselves and do a proper line shape analysis, we could very nicely follow the relative amount of protons which undergo this kind of dynamical averaging, which max out at approximately 60 GPa, and at higher pressures, it gradually goes down. That does basically not mean, does this exclude the findings here, but it basically only means that even if the hydrogen bond is already symmetric, there could still be quite a significant amount of proton mobility, if you think about that, because the energy potential of the hydrogen bond tends to be quite flat, but still quite broad. So, and then also what we did is we also went to low fields, so in the range of what we would call now dipolar-driven NMR, with an electromagnet which we recently got back at this time. And here we saw that at magnetic fields of only 400 millitesla, we suddenly observe an onset of these additional signals here, which are actually known to be tunneling sidebands, which actually become quite sharp at 125 millitesla. I have to say, this last experiment took quite a while because 125 millitesla is actually not so much to polarize your spin. So I think this was like 1 or 2 days of pure accumulation. So, and having seen that in ice, we also went for other systems, for example, in delta aluminum OOH, where we also saw the transition towards the symmetric H-bond at approximately 17 GPa, basically also by looking at the resonance spectra here. And this transition by now has already been confirmed by neutron diffraction from a Japanese group. I forgot the names, unfortunately, but it was actually quite nice because it showed us that we are not too far from the real thing. Okay, so a next experiment we've been doing was actually initiated by Viktor Strushkin, or at least the idea came from him, which is basically focused about metal hydrides. And of course, we all know why we should have a look into metal hydrides, because these kind of compounds are supposed to hold the key for room temperature superconductivity. But if we are in this kind of field, there are a couple, we are basically in a kind of awkward situation. Because on the one hand, our theoretical body of understanding is quite extensive. So we know a lot of theoretical high pressure phases of hydrides with a lot of hydrogen in their structures. And we also kind of can estimate the TC these would have. But if we really have a look at the actual experimental body of evidence, we are basically stuck at only a handful of experiments. I have to say, when I did this kind of figure early on this year, I already missed out 2 experiments, and by now there are, I think, 4 more, so we are getting somewhere. But that doesn't mean that the experiments are actually easy. The problem here is that we can actually only probe TC at the moment by doing resistivity measurements. So worst case scenario would be a a 2-point probe, or in the best case, a 4-point probe. But then the problem is that the experiments becomes very, very messy because hydrogen, which we need in order to induce the synthesis to form these kind of structures, tends to diffuse into diamonds, tends to break the diamonds, tends to compromise the electrodes, and so on and so on. On the other hand, with a resistivity measurement, we can only probe bulk properties of our sample. So at the moment, we do not really have any kind of spectroscopic method to have a look at the electronic properties of hydrogen itself. And of course, we can do that very conveniently with NMR because hydrogen nuclei are the most sensitive nuclei in NMR spectroscopy to begin with. So we thought to start out with something easy. So we started out with FEH. So since we know the synthesis and since we know the crystal structure of FEH quite well, we can actually control the actual hydrogenation of our samples quite nicely. So, and also since FEH is not known to show any kind of long-range magnetic order above 25 GPa, we also gathered that we should be able to do NMR without big issues. So now what we basically did is we prepared 2 cells, filled them with paraffin oil as a hydrogen donor, and sprinkled some iron powder on top of that. Then we closed the cell and pressurized it above the ferromagnetic collapse of iron and measured the proton signal, which you can see here. So this is a very characteristic spectrum of paraffin oil with nothing fancy happening at the moment. So, and then we took these cells and put them into a double-sided laser heating system in our house and cooked the sample at about 1200 K. And immediately after synthesis, we saw an onset of a second spin system, which was shifted by 1200 ppm, which is of course quite a bit, especially when we're talking about hydrogen. But considering that the spin lattice relaxation time of that little thing is also more than an order of magnitude lower, so much, much faster than that thing, we could already think about whether or not this is really coming from something metallic. So, and also doing synchrotron X-ray diffraction in these cells confirmed that we have a considerable amount of FCC, FEH in our sample cavity. So we basically attributed that signal to our metallic FEH. And then the experiment basically was straightforward. We measured shift as well as relaxation times for this little thing here, up to 200 GPa. So, and then being an NMR spectroscopist doing NMR on metals, the first thing I usually do is I put everything into the so-called Corringa ratio. So the Corringa ratio tells you that if you would square the shift, so basically the difference from this peak to this peak, and divide it by the relaxation times, you end up with something which is only dependent on natural constants, which should in fact be volume independent, which is apparently not the case. So at that point, we were actually almost at a loss, and we decided to have a closer look at the actual night shift. So the night shift in the metal is basically proportional to the density of states of the conduction electrodes at the Fermi surface, where we would, of course, especially in FEH, consider the contribution from the transition metals, so from the iron, to be much more dominant than the contribution we would think from the hydrogen. So the first thing we did in that case is we plotted the relative changes in K against relative changes in V into a double logarithmic power plot. And the nice thing about that is that we can basically compare scaling behavior. So, and here are these kind of diagonal strips here, which are guide to the eye for you for a Fermi gas-like kind of volume behavior. So this basically is the scaling of V to the 2/3. And the first thing we can see here is that between 30 GPa and 60 GPa, as well as 1 megabar and 2 megabars, we are basically very close on this kind of metallic slopes. Whereas between 60 GPa and 100 GPa, we are basically deviating from that quite a bit. So at that point, without any kind of ab initio DFT calculations, you would think that there's something funny happening, maybe a Lifshitz transition or whatever. But thankfully, we were able to shake our theorists in the house who were able to calculate for us the density of states for all involved electrons. And at first, let me show you what the 3D electrons are doing. And we actually found that the 3D density of states, the density of states for the T2G electron for iron basically very, very closely follows our experimental data, which was extremely nice for us to see. But now you might ask, what's then actually the contribution of hydrogen? And in order to see that, we also calculated what? Yes, yes. We are actually also not very sure about that, but this is also something we see in other hydride phases. So, yeah. So, and in order to check what's happening with the hydrogen, we also calculated that for FCC iron, where we basically saw no volume effect whatsoever in the 3D density of states. So we basically thought that there must be something also happening on the hydrogen side, and here it turns out that this thing is actually also increasing by approximately 20%, which is not very much, considering the initially very small value of the density of states of the hydrogen to begin with, but it at least qualitatively explains the small offset we see here between our data points and the 3D T2G density of states. And at that point, we also thought that there might be something funny happening on the charge distribution. So we also calculated the electron localization functions. And what we basically found is that at the point where we have the first deviation from our free electron gas model, we are basically forming these kind of pockets of free electron gas. So we are partially localizing electrons, which of course leads to this deviation from a nicely metallic behavior here. And these pockets are actually combining towards an intercalating sublattice of free electron gas, combining all of the hydrogen atoms in our crystal structure. So after seeing that, we realized that that might even be the formation of that metallic hydrogen sublattice, which is anticipated in metal hydrides, which is actually thought to be the driving force of this high temperature superconductivity we see, for example, in superhydrides. So, of course, apart from FEH, we could also have a look at other systems, for example, like copper hydrides. Copper hydrides are very nice because we have basically 3 stable hydrogen phases within 100 GPa, with increasing hydrogenation. So we have a phase of 14%, 50%, and 100% hydrogenation. So, and the experiment is basically the same. We measure shift and relaxation times, plot everything into a power plot, which you can see here. And here again, we have this trigonal phase of copper 2H, which basically seems to behave exactly like what we just saw with FEH, even with this small kink here. And we can also use this kind of plot to identify, to see that these 2 other phases, so this hydrogen deficient phase as well as this FCC phase of 100% hydrogenation, are basically not behaving like a metal at all. So, and since there were such striking similarities between our copper 2H and our FEH, we thought that there must also be something else happening in terms of the actual line shape. And it turns out, if we have a closer look at the line shapes, we found that with decreasing hydrogen-hydrogen distance, so basically increasing pressure, we are at first on a 1/r³ kind of dependence, which is basically known in NMR because it's basically dipolar proximity broadening. Because you're having spin 1/2 nuclei, which you push closer to one another, so your signal basically gets broad. And then between 2.5 and 2.4 angstroms of hydrogen distance, we suddenly observe that the resonance lines drastically collapse. And if something like that happens, we are typically thinking about some kind of a dynamic averaging Also keeping in mind that since last year or 2 years ago even, John Tse and I think also Russell Hamley proposed that the hydrogen sublattice can actually show some significant hydrogen mobility under increasing pressure. We can actually use that idea to very nicely explain these observations basically by that. So at first we start out decreasing our line, decreasing our distances, which basically leads to a significant broadening of our line. So this is a theoretical Pake doublet which you would get from dipolar broadening. And then after a certain point when the atoms begin to move about, we are basically averaging out the dipolar interaction, which leads again to an averaging out of our line width, which is basically we think we see here. At the moment, we are also running some MD calculations on the diffusion coefficient of hydrogen atoms themselves, and it turns out that at least the order of magnitude which we get from the diffusion coefficients for hydrogen as in kappa 2H as well as in FEH are very close to what we would extract from that kind of behavior. Okay, but so much for metal hydrides. Another thing we've been doing since beginning of this year was actually initiated by that paper. So this is a paper from April 1st from Bartomeu Montserrat and Chris Picard. And they actually argue that NMR might be the only spectroscopic method where we can resolve the issue of the high pressure phases of hydrogen. Because what they basically realize is if you are able to calculate the chemical shielding tensor and then the chemical shift, you find out that the the theoretical high pressure phases do actually show a significant variety of possible NMR spectra. That of course means if we want to do NMR in that case, we need a resolution, or we need a method to increase our resolution so that we can resolve chemical shift differences. So, and of course, when we're talking about hydrogen itself, it gets a bit messy because, as you can see, in time domain, the signal decays actually very, very fast. So here the signals are already gone after 15 microseconds. If you do a Fourier transform of that thing, you end up with something which is 5,000 ppm broad. Typically for chemical shift analysis, you need something which is 3 ppm, 1 ppm. This is typically what high resolution NMR techniques are doing. So, but thankfully NMR has a couple of tricks upon its sleeve. For example, magic angle spinning, where we can basically rotate the sample in the magic angle and rotate it then very, very fast, which leads to a cancellation of the dipole-dipole interaction. But of course, we cannot really do that with our diamond cells because they weigh approximately 300 to 400 grams. They are quite bulky, and we should be able to rotate it with such a broad line of 150 towards 200 kilohertz of physical rotation speed, which of course we cannot do. But of course we can also go the other way around and basically force the spin system to go into the magic angle. And we typically do that with a very, very old NMR experiment called the Lee-Goldberg decoupling. So here what we are doing is we are irradiating the system with a low amplitude and off-resonant pulse, which is set in a way that we force the spin system into an arbitrary angle. Then we let it for a certain time t2. And then immediately afterwards, we do an excitation pulse and look at the intensity coming out. So what we are doing then is we plot the intensity of that thing against the increments here, and we get a so-called free induction decay and the rotating frame. If we do that, we are actually able to stretch our free induction decay by 3 orders of magnitude if we do it properly and basically hit the magic angle to a very nice degree. And of course, if you do a Fourier transform of that thing, you end up with something which is only 3 ppm broad, which is exactly the range where we want to be in order to resolve chemical shift differences. So, and this was actually the first experiment done in the diamond endocell where we were actually able to show that we can do this kind of methods for high resolution experiments, which could be regarded as a first step towards something called NMR crystallography, where you can really have a look at, for example, more complex structures than simply hydrogen. So, and by now you might have already guessed what we are basically up to, which is hydrogen itself. So from a physicist's point of view, hydrogen is of course quite interesting, because even in this free quantum rotor phase, so which is stable up to 120 to 180 GPa, where we're having these hydrogen molecules arranged in a hexagonal lattice, we are having the nice effect that the intramolecular distances are way below the thermal de Broglie wavelengths. So we basically need to add the nuclear spins in a way that we basically have one spin isomer having three energy levels, the so-called orthohydrogen, and one spin isomer which only has one energy level, the parahydrogen. If we compare that with a system of isolated hydrogen atoms, so for example in the metal hydrides we would have that, you could see that there are some kind of funny things happening. And of course we will always have kind of a thermal relaxation between this orthohydrogen and the ground state, which is widely considered the parahydrogen. So, and now if we think about inducing NMR transitions in such a system, we would actually be faced with three different regimes. Whereas on the one hand, we have something which we cannot see at all. So parahydrogen has a spin 0, we cannot see it. Orthohydrogen, since it has three energy levels, it effectively works as a, as a quadrupole system, and if we are lucky, even only with a quadrupole system in first order. Whereas a system of isolated hydrogen atoms is basically dipole-dipole interaction. So, keeping that in mind, there is mounting theoretical evidence at the moment that with increasing pressure, we are basically hindering the free quantum rotors in, well, rotating, which basically would mean lead to at a certain point that we cannot really define J as a good quantum number anymore. So, and of course there are a couple of funny things happening in Raman. So the big question now is what happens with the spin system at all. So, and we've done first experiments up to 130 GPa. And again, these are very preliminary results at the moment. And let's at first look at the chemical shifts. So these are chemical shifts which we were able to extract after properly Goldberg decoupling. And what we found is that we're basically following a squared dependence with a minimum at approximately 50 to 60 GPa, which is reasonably close to the observed overtake, which we also see in Raman. On the other hand, the spin lattice relaxation times are typically very flat in the order of 10 to 20 milliseconds, which is quite nice because we can use that in order to accumulate spectra very, very fast. Also, when we have a look at the static NMR spectra, we can see here, we see it's basically very broad, more or less featureless. But then we went over 70 GPa and something funny happened, which we could at first see in the chemical shift here. So there is a kind of deviation from this square root dependence here. On the other hand, the spin lattice relaxation time also jumps by a factor of 2. And more importantly, the actual proton resonances are suddenly approaching something which kind of looks like a dipolar Pake doublet. So the big question now is what's actually happening. And in order to emphasize this transition a bit more, I plotted the relative changes again of the line width against density. And suddenly we saw that at approximately 70 GPa, we are following a 1 over r cubed dependence. So now the question is, where is that coming from? Why can it be 1 over r cubed? And of course, a possibility could be that we are basically reducing the intermolecular hydrogen-hydrogen distances up to a way where we might think about whether or not it is really reasonable to add up nuclear spins in a single molecule or not. So we basically end up with the question, is this dipolar or is it quadrupolar? So in the next weeks, we are planning on doing something called a two-dimensional notation spectroscopy. at increasing pressures, where we can very nicely distinguish contributions from an isolated spin 1/2 system, so a dipolar system, and the quadrupolar contributions, because we would basically have the distinction between a spin 1/2 and the spin 1. So, but enough of that from the hydrogen side. So, a last thing I want to show you is from a more technical perspective. So since I started in BGI, it was always the question of how can we make the complete method more accessible to other high-pressure NMR groups. And after looking around for like small and affordable magnet designs, I found a company in the UK selling these kind of magnets. This is a so-called Halbach array magnet. This magnet is incredibly strong. It makes a magnetic field of 1 Tesla in the midpoint. And after we exchanged a couple of emails, they were able to manufacture one of these Halbach array magnets for us with a hole in the middle which is big enough so that we can basically just put one of our BX90s in there. Then we have a cable connecting the resonator in the midpoint, going towards something like that. It's basically a very, very, very rudimentary NMR probe. This is basically 2 capacitors, that's it. Then we connect it back to our modular NMR spectrometer. So, and the first thing when you have something like that is, of course, you need to figure out how inhomogeneous your B0 field is. Because you can imagine, if the magnet is only 4 centimeters high, if there is a sweet spot, it will be very small. And in order to see that, we prepared a cell with I7 up at approximately 20, 25 GPa, and basically just shifted the cell along the main axis from here to here. And we basically found a sweet spot of approximately 1 to 2 millimeters, which is, in terms of proper NMR experiments, terrible. But we gathered that for our diamond cells, it's actually good enough, considering that the height of our sample cavity is typically not bigger than 15 to 20 microns. So, and this is actually a resonance spectra we got at the magnetic sweet spot. It's reasonable. It's not completely nice, but that's actually nothing you would actually expect to happen. So, and the good thing we can also do with that setup is we can basically put it in on a double-sided laser heating setup and try to do NMR at high pressure while we are doing laser heating. And this is exactly what we did. And one of the first things we need to, of course, consider is that at high temperatures, we are depolarizing the magnetic polarization. So we are killing magnetic polarization. On the one hand, we are increasing the noise level on the other. So basically, signal to noise goes down quite a bit. The dependence is actually with 1 over t to the 3/2. So, no, 5/2. So it basically goes down very, very rapidly, as you can see here. So this is at room temperature. This is the same experiment at laser heating. As you can see, thermal noise voltage goes up. The signal noise voltage, the signal voltage basically goes down. But the good thing is we can actually use the loss of the signal to noise in order to estimate our temperature, which is in the order of 1000 K. So, and here on the right-hand side, you can see actual resonance spectra. So this is before heating. This has been done while we have been heating. So the whole experiment basically did not last longer than approximately 30 seconds, because heating for such a long time is actually quite dangerous for diamonds, which we unfortunately found out in the next experiment, because then the diamonds basically cracked open. But we were still able to get a nice signal at the 1000 K. Whether or not this signal is coming from something liquid or if it's a solid, maybe a superionic, we don't know yet. We are still preparing another set of experiments, and hopefully we can even get a PhD student doing that for us. So that's about almost everything I want to tell you. Yeah, I have basically 3 take-home messages for you. So doing NMR in the diamond cell is actually not magic at all. We can do that up to 200 GPa by now. And there is actually a theoretical prediction from the KIT group that the theoretical detection limit is in the order of 0.03 picoliters of pure hydrogen. That is a sample volume which we typically have at double-stage or toroidal diamond anvil cells. This is something we should really keep in mind for future experiments. On the other hand, with this homonuclear decoupling experiment I just showed you, we are actually on the brink of something which might be much more interesting for the geophysical community, so not only something for to please physicists. So, and also with the development of this tabletop system I just showed you, we hope that we are able to reach out to other high-pressure NMR groups who are actually willing to go into that direction with a relatively affordable high-pressure NMR setup. And also another nice thing we can do is we can basically take the magnet and take the spectrometer, put it on site on a synchrotron and basically synthesize new samples, do X-ray spectroscopy to see the structure, and also do already a first preliminary NMR experiments on that. So as for acknowledgements, there are of course a lot of people I want to thank, and predominantly Leonid and Natalia, who are basically my mentors at the moment. And then I'm also very thankful for the help of our two theorists, so Florian Trübel and Gerd Steinle-Neumann, who were the two guys doing our DFT calculations. So, and then, of course, I'm also very thankful for the help of the group of Professor Jan Korvink, who introduced me into the field of the lenses. So, thank you very much.
In your water study, I was interested in whether you had polycrystalline ice or a single crystal of ice.
That's actually a good question. I would doubt that it is single crystal, considering that we ramped up the pressure very, very quickly. So we basically just by the turn of a screw, there's no real reason to believe that we are forming single crystals. We have a couple of people in BGI who spend like 5 to 6 years trying to make single crystals of ice, one of the low pressure phases.
Right.
Never really did it. It was always crystalline.
Well, so this is my second question, and this is what confused me when I first read your paper. First of all, I want to compliment you on this because it's extraordinarily interesting, and I completely agree with you that if you can do NMR of hydrogen, solid hydrogen, you have a much greater chance of extracting the kind of information you need. But aside from that, so with your water study, I expected to see a powder, opaque powder pattern, because I figured you probably have a lot of randomly oriented small crystallites, and so, but you don't really see a opaque powder pattern. Why is that?
That's actually a good thing. The first, I was also expecting that, because what you would actually get for, or what is already known for the hexagonal phase, so 1H, when you simply have water, cool it down, and then slightly above the melting temperature, you can still do NMR. You get a broad powder pattern, like 500 kilohertz, like a fat Gauss. So, and when we saw the first signal at at approximately 10 GPa of I7, we had something extremely sharp. So it was only like 100 ppm, compared to 500,000 ppm, which you would get for like 500 kilohertz. So that was actually the first thing where I thought that there might be something dynamic happening. So that was actually my first step in looking all of the literature, what could happen in ice. Because I wasn't aware of the effect of hydrogen bond symmetrization and whatsoever. So at the moment we are very sure that there must be some kind of collective dynamical effect, which we can also see in delta aluminum OH. There we also have a very sharp signal, which we wouldn't expect in the first place.
So I haven't studied. But I guess the other issue would be that.
Yeah, that is also what we at the moment believe happens in hydrogen itself, where actually in hydrogen it's much worse because the compressibility is so high. We ramp up the compression so fast. I mean, within 10 GPa, it already increases by a factor of 5, So we have a 5-fold compression, whereas in ice we have like 20%. So
Thanks. Yeah, very interesting work. So with the hydride study, you were showing some slides. You were trying to explain the trend with the density of states at the Fermi level, and you're showing some localized versus delocalized charge. We know a lot of these things are non-stoichiometric, so I'm just wondering what the role of stoichiometry and how that might change with pressure could be used in that interpretation.
Perhaps. At the moment, I have to say we don't have enough data to really put any systematics in there. We are just starting experiments on sulfur. We're about to start experiments on yttrium and lanthanum to go into the really crazy systems. We cannot say yet. I mean, for copper as well as hydrogen, we were really sure about the stoichiometry because we could basically confirm that with X-ray.
Well, that's also challenging as well. By the way, you also heated oil, right? So the carbon can also interact with metals and form carbide. So that might be another thing to consider.
That might be another thing. And fortunately, we might have the possibilities in the near future to load directly hydrogen, and to do it with hydrogen.
Right. And then just maybe you can comment briefly on, I really liked the way you were kind of going out to very long times before you do the Fourier transform to try to get higher resolution, but maybe you can comment on, what are the prospects for other nuclei and how we might use this technique to obtain more chemical information like we would do in traditional magic angle spinning NMR.
We are currently preparing the first experiments with silicon oxide, so a single crystal of SiO2, where we are basically hoping to see a change in coordination number. Of course, with SiO2, when we are measuring the silicon resonances, it's kind of cheating because the chemical shift spread is much bigger than it is for hydrogen. So with silicon, we might not have the same issues, but we actually want to see it also with some low gamma nuclei. So silicon is in my list of experiments. With aluminum, it should actually be the same. With aluminum, we should also be able to see that. But again, I simply do not have the workforce to do it.
So how do you know, how can you determine whether you're always probing the same region of your sample chamber?
That's the beauty of NMR. You're always sampling all of the sample chamber.
And is the B1 field uniform enough to?
That is of course, exactly the question, yes. Typically what you do, or typically what other NMR people are doing when they want to quantify the homogeneity of the B1 field is they do a notation experiment. So they basically increase the pulse length and look at the intensity coming out. So, and typically for a pure dipolar system, so spin 1/2, it should be a sine wave. So if you're lucky, your amplitudes do not deteriorate so much. In our case, we have one pronounced maximum at low pulse angles, and then it already goes down. And then you're having the problem that at even longer pulses, so more energy you put into the system, you're basically exciting the hydrogens around. For example, the excitation coil is covered with polyurethaline. You're exciting these hydrogens at some point. So basically you have one maximum, one small, and then it goes up. So we can actually consider the B1 field to be quite inhomogeneous. This is a problem which we always have, but the question is whether or not you really want to invest like 2 or 3 PhD lifetimes of solve that issue without measuring something meaningful, or if you just go with what you have and be happy with it.
Well, what about collecting data on decompression? Would that help?
We did that. The copper hydride, I have to admit I was really nasty to these cells. So we went up to 30, did laser heating. We already saw the first cracks. Went to 100, did another laser heating. The diamonds weren't very happy about that. And then we decompressed down to 15. So possible, it's doable. It's basically not much more difficult than with other cells, with regular cells.